Hey, what's up, guys? This is me, Bjorn, a member of the Group 4 in Fluid Mechanics, and we are going to talk about external flow. But first, we are going to share our objectives. So let's begin.
Hello everyone. So for today, we are now already in the module 6 of our discussion in fluid mechanics, which tackles about the external flow, especially the drag and lift. So before we start, looking at the photos, could you tell what classification of fluid is demonstrated by the movement of unbounded fluid over these surfaces? Yes, that's right. So, such motions are referred to as flow over bodies or external flow. So, let us define what is an external flow. So, external flow, this is characterized by a freely growing boundary layer surrounded by an outer flow region that involves small velocity and temperature gradients. Also, fluid flows may be over a stationary body, such as the wind blowing over a building, or in other times, a body moves through a quiescent fluid, such as a car moving through air. So we move on. Also, a flow can be classified as being steady or unsteady depending on the reference frame selected. Flow around an airplane, for example, is always unsteady with respect to the ground, but it is steady with respect to a frame of reference moving with the airplane at cruise conditions. And lastly, developing a good understanding of external flow is important in the design of many engineering systems such as aircrafts, automobiles, ships, submarines, and all kinds of turbines. When a fluid moves over a solid body, it exerts pressure forces normal to the surface and shear forces parallel to the surface of the body. As you can see in the photo illustrated, the component of the resultant pressure and shear forces that acts in the flow direction is called the drag force or just drag, which is characterized by FD or friction drag, which is the arrow pointing to the left. And the component that acts normal to the flow direction is called the lift force, or just lift, which as you can see in the photo is illustrated by FL or friction lift, which is the arrow pointing upwards. So moving on, fluid flow over solid bodies frequently occurs in practice, and it is responsible for numerous physical phenomena, such as the drag force on automobiles and the lift developed by airplane wings.
The external flow in free stream velocity. The flow fields and geometries for most external flow problems are too complicated to be solved analytically, and thus we have to rely on correlations based on experimental data. The velocity of the fluid approaching a body is called the free stream velocity and is denoted by V. It is also denoted by U infinity or capital U infinity when the flow is aligned with the x-axis, since U is used to denote the x component of velocity. The shape of a body has a profound influence on the flow over of the body and the velocity field. The flow over a body is said to be two-dimensional when the body is very long and of constant cross-section and the flow is normal to the body. The wind blowing over a long pipe perpendicular to its axis is an example of two-dimensional flow. Note that the velocity component in the axial direction is 0 in this case, and thus the velocity is two-dimensional.
Hi, I'm Christy Mabale from SC11. So let us continue the discussion. So the picture above is an example of two-dimensional flow. So the two-dimensional idealization is appropriate when the body is sufficiently long so that the end effects are negligible and the approach flow is uniform. So in this picture below, let us guess what kind of flow occurs in a bullet bursting through air. So the flow that occurs in a bullet bursting through air is an example of axisymmetric flow. Axisymmetric flow is another simplification of two-dimensional flow that occurs when the body possesses rotational symmetry about an axis in the flow direction. The velocity in this case varies with the axial distance that denotes small letter x and the radial distance that denotes small letter r. But when the flow over a body cannot be modeled as two-dimensional or axisymmetric, it is three-dimensional flow. The example of three-dimensional flow is a flow over a car. Flow over bodies can also be classified as incompressible and compressible flows. Compressible flows like flows over high-speed aircraft, rockets, and missiles, while incompressible flows like flows over automobiles, submarines, and buildings. The compressibility effects are negligible at low velocities. Flows with Mach less than or approximately to zero point 0.3, such flows can be treated as incompressible with little loss and accuracy. There are two bodies subjected to fluid flow that has been classified that depends on their overall shape. Streamlined and bluff are the two bodies subjected to fluid flow. A body is said to be streamlined if a conscious effort is made to align its shape with anticipated streamlines in the flow. Also, streamlined bodies appear to be contoured and slick, like race cars and airplanes. While a body, such as buildings, tends to block the flow is said to be bluff or blunt.
So now, let's talk about drag. Drag is the force a flowing fluid exerts on a body in the flow direction. In order to have drag, there must be motion between the object and the fluid. If there is no motion, there is no drag. It makes no difference whether the object moves through a static fluid or whether the fluid moves past a static solid object.
So the benefits of drag are friction, for example, in which it acts as a lifesaver in the brakes of automobiles. Also, it makes possible for people to parachute, help pollens to fly in distant locations, and for us all to enjoy the waves of the ocean. Scientists find ways to reduce the effect of drag. One of the examples is the reduction of drag is closely associated with the reduction of fuel consumption in automobiles, submarines, and aircraft. They also improved safety and durability of structures subjected to high winds. And lastly, reduction of noise and vibration. Other examples include a bicyclist riding a bike, a boat moving through, or the analytical technique of electrophoresis, in which it is a laboratory technique used to separate DNA, RNA, or protein.
Additional information. The drag force can be measured directly by simply attaching the body subjected to fluid flow to a calibrated spring and measuring the displacement in the flow direction.
More sophisticated drag measuring devices called drag balances use flexible beams fitted with strain gauges to measure the drag electronically.
Drag reduction, it is a physical phenomenon that causes friction to be reduced and fluid flow to be increased. A reduction of just a few percent in the drag that acts on an air vehicle can translate into large reductions in fuel weight and operating costs. One approach to achieve such reduction is to active control naturally occurring streamwise vortices in the viscous sublayer of the turbulent boundary layer at the vehicle surface. But up to 25% reductions in the wall shear stress are possible by properly controlling the structure of the turbulent boundary layer at the vehicle surface. This is a powerful nonlinear system capable of amplifying small microactuator-induced perturbations into large reductions in the vehicle drag. The challenge has been to develop large, dense arrays of microactuators that can manipulate the structures to achieve drag reduction on particular aeronautical and hydronautical vehicles. And lastly, sublayer structures are typically a few hundred microns and thus well matched to the scale of microelectromechanical systems.
So in this picture presented in the presentation, it is the microelectrokinetic actuator array, or the MECA5, with 25,600 individual actuators at 325 ohm, spacing for full-scale hydronautical drag reduction, close-up of single unit cell at the top, and a partial view of the full array is the bottom. An example of one type of such microscale actuator array based on electrokinetic principle that is potentially suitable for active sublayer control on real vehicles. So the electrokinetic flow provides a way to move small amounts of fluid on very fast time scales and very small devices. Actuators impulsively displace a fixed volume of fluid between the wall and the viscous sublayer in a manner that counteracts the effect of sublayer vortices. So the system architecture provides greatly reduced control processing requirements within individual unit cells, which consist a relatively small number of individual sensors and actuators. Also, scaling principles governing electrokinetic flow, sublayer structure, dynamics, and microfabrication technologies have been used to develop full-scale electrokinetic microactuator arrays that can meet many of requirements for active sublayer control of turbulent boundary layer under real vehicle condition that may in the future allow engineers to achieve dramatic reductions in the drag acting on practical aeronautical and hydronautical vehicles.
So under friction and pressure drag, we have reducing drag by streamlining. The first thought that comes to mind to reduce drag is to streamline a body in order to reduce flow separation and thus reduce pressure drag. But let us know first what is streamlining and what is its significance. So streamlining, this is the process of reducing turbulence by altering its design. To do this, we can change the shape, the material, and the surface features of an object. So as you can see in the photo provided, observing a disc, you can see that it has a large turbulent wake. And as we elongated the disc and formed a sphere, you can notice that the turbulence wake has decreased, which has become smaller. And as we elongate more the sphere, we then have a teardrop shape. And you can notice that its turbulence wake has become really small compared to the original wake that it has when it was still in a disc shape. So streamlining's main goal is definitely to reduce drag. However, streamlining though has opposite effects on pressure and friction forces. It shows that the more you streamline an object by elongating its rear surface, the more you reduce the size of its wake and the resulting pressure drag. But elongating an object increases its surface area and thus increases the effects of friction drag. So the effect of streamlining on the drag coefficient is described best by considering long elliptical cylinders with different aspects or length to thickness ratios, or L over D, where L represents the length and the flow direction and D is the thickness. So let us describe the photo provided. As you can notice, the drag coefficient decreases drastically as the ellipse becomes slimmer. As the aspect ratio is decreased and the cylinder resembles a flat plate, the drag coefficient increases to 1.9, the value for a flat plate normal to flow. Note that the curve becomes nearly flat for aspect ratios greater than about 4. So the reduction in the drag coefficient at high aspect ratios is primarily due to the boundary layer staying attached to the surface longer and the resulting pressure recovery. The pressure drag on elliptical cylinder with an aspect ratio of 4 or greater is negligible, or less than 2% of the total drag at this Reynolds number. Next, streamlining has the added benefit of reducing vibration and noise. But remember, streamlining should be considered only for bluff bodies that are subjected to high velocity fluid flow, and thus high Reynolds numbers, for which flow separation is a real possibility. And lastly, streamlining is not necessary for bodies that typically involve low Reynolds numbers, since the drag in those cases is almost entirely due to friction drag, and streamlining would only increase the surface area, and thus the total drag. So to wrap everything up, basically streamlining is used to reduce pressure drag by altering the design of an object. So remember, the more we elongate the rear surface of an object, the more its pressure drag will be reduced. However, doing this will result to an increased friction drag. So basically, they have an inversely proportional relationship here, because reducing the pressure drag increases the friction drag. And this is how streamlining works in reducing drag. So that is all for my topic in reducing drag by streamlining. Thank you.
So we must get familiar with boundary layer creation in order to comprehend flow separation, which I trust you are already aware of. So when forced to flow across a curved surface at high speeds, a fluid responds in a similar manner. The front part of the curved surface is followed by a fluid with no issue, but on the back side, it struggles to stay affixed to the surface. At sufficiently high velocities, fluid streams detaches itself from the surface of the body. When the fluid's change in velocity, either in magnitude or direction, is too great for the fluid to attach to the solid surface, flow separation, also known as boundary layer separation, takes place. The most major effects in the boundary layer are those of separated region and wake. When a fluid separates from a body, it forms a separated region between the body and the fluid stream. This area of low pressure behind the body, a separated region, is one where backflows and recirculating occur. Reduced velocity is one of the downstream consequences of flow separation. With reference to upstream velocity, the wake is the area of flow behind a body where the body's effects on velocity are felt. Complete separation over the entire back surface may also occur in a streamlined body, such as an airplane wing at a sufficiently large angle of attack larger than about 15 degrees for most airfoils, which is the angle the incoming fluid stream makes with the cord, the line that connects the nose and the trailing edge of the wing. Flow separation in a wing-stop surface substantially reduces lift and raises the possibility of an airplane stall. Numerous aviation accidents and decreased efficiency in turbomachinery have been attributed to stalling. Keep in mind that lift and drag are highly correlated in the body's form, and any impact that has a significant impact on the drag and lift when it causes the form to shift. For instance, the buildup of snow and the formation of ice on airplane wing may significantly alter their shape and reduce lift. Many aircraft have lost altitude and crashed as a result of this phenomena, while many more have aborted takeoff. As a result, prior to takeoff in inclement weather, it has been standard procedure to inspect vital airplane components for ice or snow accumulation. This is crucial for airplanes that had to wait on the runway for a while before taking off due to heavy traffic. One significant impact of flow separation is the vortices. It is the formation and shedding of circulating fluid structures in the wake region. The periodic generation of these vortices downstream is referred to as vortex shedding. This phenomena typically happens during normal flow through large cylinders or spheres. When designing equipment that is exposed to high-velocity fluid flow, such as an airplane wings and suspended bridges exposed to steady high winds, it is important to keep in mind that the vibrations produced by vortices close to the body may cause the body to resonate to dangerous levels if their frequency is close to the natural frequency of the body.
Once we say lift, it is the components of the pressure and wall shear forces in the direction normal to the flow tend to move the body in that direction and their sum. Once we say lift, the components of both the pressure and the wall shear forces in the direction is normal to the flow, wherein it tends the body to move to a specific direction. As we can see in the figure 11 to 5, the moment about the flow direction is called the rolling moment. The moment about the lift direction is called the yawing moment. And the moment about the side force direction is called the pitching moment. The lift coefficient is defined as the lift coefficient is equal to C sub L is equal to F sub L divided by 1/2 of PV squared times A. The drag and lift coefficients are primarily functions of the shape of the body, but in some cases, they also depend on the Reynolds number and the surface roughness.
Friction and drag pressure. When a body moves through a fluid or a fluid flows through a body, drag forces act on the body. These generally have two causes. Shear stress, which is called the frictional forces, or the normal stresses, which also called the pressure forces. The part of the drag that is due directly to wall shear stress is called skin friction drag or just friction drag, since it is caused by frictional effects. Drag coefficient is equal to drag force over 1/2 density times velocity squared times reference area. When the friction and pressure drag coefficients or forces are available, the total drag coefficient or drag force is determined by simply adding them. Drag coefficient is equal to friction drag coefficient plus pressure drag coefficient. And drag force is equal to friction drag force plus pressure drag force. The friction drag is the component of the wall shear force in the direction of flow, and thus, it depends on the orientation of the body as well as the magnitude of the wall shear stress. The friction drag is 0 for a flat surface, normal to the flow, and maximum for a flat surface parallel to the flow, since the friction drag is in this case equals to the total shear force on the surface. Therefore, for parallel flow over a flat surface, the drag coefficient is equal to the friction drag coefficient, or simply the friction coefficient. Friction drag is a strong function viscosity and increases with increasing viscosity. Reynolds number is inversely proportional to the viscosity of the fluid. Therefore, the contribution of friction drag to the total drag for blunt bodies is less at higher Reynolds number and may be negligible at very high Reynolds number. You're curious what is Reynolds number? Reynolds number is basically the ratio of inertial forces to viscous forces within a fluid which is subjected to relative internal movement due to different fluid velocities.